Hello, everyone. Thanks for joining another Cyber Skyline Live. I am Franz Payer with Cyber Skyline, and I'm here to help you learn about cybersecurity. We run these episodes for you, so please stick to the end and let us know what topics you want us to cover next. This week's topic is reverse engineering basics. So I'm going to jump into my slides, but while I do so, please make sure that you ask any questions that you have during today's episodes in the chat. We will circle back to them and answer them as we go through today's show. So, without further ado, let's talk about reverse engineering. So, reverse engineering is the process of attempting to understand how a piece of software works by using deductive reasoning. That's like the textbook Wikipedia definition. Basically, the idea is that someone has written some code and you are analyzing whatever is remaining of that code. That code could have been modified and manipulated in a way to make it more efficient, which causes some challenges in understanding what is going on. And even if you are able to find the original thing that they typed in for their code, you aren't them. They might not have documented some information which is necessary to help you understand how the code works. And I often compare reverse engineering to trying to understand someone's notes. Sometimes they're easy to read. Sometimes the notes are very well documented. It's very clear, very self-explanatory. And sometimes they might use a lot of shorthand, and you don't understand what these abbreviations mean, or maybe their handwriting is bad. You don't quite understand it. Or sometimes it's in a different language. What if you were asked to read someone's notes and it wasn't even in your native language? This is just to explain the fact that at the end of the day, you are analyzing something that someone created, and depending on the situation, it could be relatively straightforward and easy for you to piece together what it is that they're doing, what it is they're trying to accomplish with their code. And sometimes it's extremely difficult to understand what's going on. You might not understand the language. You might not have their comments available to help you understand how the code works. So keep that in mind when you go through reverse engineering. This is generally considered to be a more higher difficulty level topic. It requires you to understand fundamental concepts within coding. And so if you don't know how to write code very well, it's a little bit harder to be able to piece together someone else's code. So keep that in mind as you go through reverse engineering. If you don't have a very solid foundation of coding, I would highly recommend that you go through and learn how to code first before you really dive too deep in reverse engineering. A lot of these concepts in reverse engineering are difficult to understand on the fly. And so it's useful to be able to have that background knowledge before you go in. We have past episodes where we talk about coding. And so if you don't know anything about coding, I'd highly recommend you go back, check out those past episodes, and get up to speed. Now, you might be wondering why you even care to do reverse engineering. How is this even relevant? Well, there are many different applications for cybersecurity. The really big one is that if you are working in cyber defense, you might be in a situation where there's some new malware that hackers have released, and you need to understand what the malware is doing in order to create proper defenses to that malware. Or maybe you actually find a vulnerability in the malware, which allows you to neutralize the malware. Um, Being able to understand what the code is doing will really help with your organization's defense against that malware. Another use case is using reverse engineering to create a fix or workaround for some software which is wonky. So you might see this in enterprises which are using some old software. If someone wrote code like 10, 20 years ago, they're no longer with the company, or maybe you bought it from a vendor and the vendor is no longer providing support for that software, but that software is critical for the functioning of your IT environment. Well, what do? If you are able to reverse engineer that software and see what it's doing, maybe you can patch the code and fix the software. Or maybe there's something external that you can do to account for some wonkiness of that software. These skills can come in handy when you least expect them. I've seen a lot of people actually use some reverse engineering skills to fix a bug in a software program that they just use on a normal basis. They're not even trying to find a specific vulnerability. There's just a bug in the software, and they're here to fix it using reverse engineering. And then a third use case for reverse engineering is to analyze software to find vulnerabilities in a security audit. So you might reverse engineer some some software which is running on all these different devices uh, on a computer network, and it might be your job to make sure that this software is secure so that a hacker can't break in and find a vulnerability in that application and compromise all these different systems. There are specific rules with analyzing and doing secure coding to help make more secure software. So these are all great reasons uh, to build a reverse engineering skill set. Now let's go and understand, like, what types of code are you gonna be encountering when you do reverse engineering. This is a pretty big domain because the skills and the tools necessary to do reverse engineering are going to depend on the language that that code was written in. And I've got this little bit of a Venn diagram here, where we've got compiled languages and interpreted languages. These are two very common ways to categorize programming languages. And the big difference between these two is that compiled languages involve taking human readable code, so stuff that is in plain text, and then converting that plain text code into machine code. So ones and zeros, some binary code that a human can't really read, but a computer would know how to read. Those are compiled languages. And we've got some common examples. We've got Go, that's the Gopher over there, C++ and C. And we also have Swift, that's the Swift icon for the iOS apps. So these languages, the author of this language will write in a human readable format, but that human readable format is not what gets processed by a computer. That human readable format gets sent to something called a compiler, which will convert the human readable code into a machine optimized code. And the reason that people do this, one is for efficiency. The amount of, like, characters and text required for humans to convey information is much greater than the number of characters and text required for a computer to understand that information. So for example, if you wanted to say a sentence in English, every single word requires multiple characters, and they can be pretty long to convey that information. You also require spaces between those words. With computers, they can use shorthand. They can use an index instead of having, like, long words that are 10 characters long, 20 characters long for like long letters, long words. Computers can have a an index which is much more space efficient. They require fewer pieces of information to convey the same concepts. So that's one reason why compiled languages are used. Another reason is actually to obfuscate the code, to make it harder for other people to read and understand what's going on. And another reason is, specifically, computers cannot use that code outright. They actually need that to be converted into the language that they speak. And if you try to do that conversion while you're running the program, it's much slower to do that. Now, on the right side, we have what are called interpreted languages. These languages are taking a human readable text and giving it into something what is called an interpreter. So you will write a JavaScript file, you might write a Ruby file, and this text is sent to a interpreter. And while a compiler will convert the text and the human readable text, in and create computer code, the interpreter will take the human readable text and run the code. So with the compiled language, it does the conversion and the translation, and then you run the program later. And anytime you want to run the program, you have the machine version that you can run whenever you want. With an interpreted language, this happens on the fly. So there is not a file that you are specifically generating as a result of this that you run later. You actually run it on the fly. It's much less efficient, but the benefit is that oftentimes these interpreted languages are faster for a programmer to write in. They can write JavaScript code much faster than they can write C++ code, as an example. In the middle, there's actually an overlap. We've got Java and we've got Ethereum, which these languages actually are hybrid. The Java code that you write goes into something called the JVM, the Java Virtual Machine, and the Java Virtual Machine will run that code. The reason why it's in this hybrid is because you actually need to convert the human readable Java code into what is called bytecode. This is the code that the Java VM will take and run. So the Java VM is actually interpreting this bytecode, but the 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 code that you write in Java is not immediately being turned into the ones and zeros, the binary that the computer can run by itself. The computer requires this Java virtual machine, which sort of acts like an interpreter, but instead of working directly on the human readable text, it's working on this bytecode. The reason for this is efficiency. It's much faster for the Java virtual machine to work on the bytecode than it is to run on the human readable plain text. And another reason why this occurs is that the Java virtual machine can run on multiple different computers. So with those compiled languages, when you compile the program, it compiles to a specific computer, to a specific operating system. So you might have compiled code which only runs on Windows, which only runs on Linux. Java code can run on multiple different types of machines because the Java virtual machine runs on those different machines. And as long as the bytecode runs on the Java virtual machine, you don't actually have to compile different versions of that program for Windows and Linux. The Java virtual machine runs on Windows and Linux, and the bytecode will go into the Java virtual machine, and you won't have to have multiple different versions for each operating system. And this is an attribute called portability. You want to be able um, to to use the same code on multiple different operating systems without having to compile it multiple times. I'm also seeing a comment in the chat. Spencer's saying, to be clear here, if the Ethereum language is called Solidity. That is correct. So Ethereum, the Ethereum virtual machine is used, but the language that plugs into the Ethereum virtual machine is called Solidity. All right. So let's dive into another concept, which is called decompiling. I mentioned previously that when you compile code, you're turning it from this plain text human readable format into these ones and zeros that the computer knows how to process. The process of going the other way around, reversing it, is called decompiling. So you compile to convert the human code into computer code, and then you decompile to go from that computer machine code back into the human readable code. That's decompiling. Now, there are limitations with decompiling. Decompiling oftentimes has less information than is available from the original source code, so it cannot perfectly one for one turn the compiled code back into the to the original source code. So a couple of these limitations, you might be missing code comments. Oftentimes, the compilation process will remove code comments, and so you can't get those back. You might also see strange variable and function names. So when compiling code, the compiler will sometimes remove those nice names that the developer created and put a very it'll actually create a machine reference to that code or to that variable. And when you decompile it, you don't have a nice name for a function or a nice name for a variable. You get some auto-generated text that the decompiler creates. You might also notice that there's different formatting and different structure from the original source code. So when the developer created the source code, they might have organized their code into multiple different files. They might have, ordered their code in a structured way. And when you decompile that code, you're gonna get it in some whatever format the decompiler spits out for you. It's not necessarily going to be the same format that the authors intended. So those are some things to keep in mind. You need to do decompiling to reverse engineer and analyze those compiled programming languages. You can't easily read that compiled machine code, right? Like I said, those are kind of like ones and zeros. That's binary data. A computer can read that, but it is extremely inefficient and tedious and difficult for a human to go and understand how to read that code. You could, if you're an expert, try to figure it out. It's very time inefficient, and it's much better to have a tool help you take that machine code and get some sort of decompiled code, which might not be perfect. It's not going to be the original, but it could at least be a lot easier to work with than that machine code, which is in binary. So let's cover a couple of tools that you'll be using when reverse engineering. The very first tool that I recommend, it's a very simple tool. It's called Strings, which comes pre-installed on Linux. And I highly recommend running Strings on any binary that you encounter. The reason for this is that Strings will extract any text that is in that binary file. That text is often going to contain information such as maybe there's an error message and you can see what the verbiage with that error message is. Maybe there is a reference to a file location or the name of other assets on the computer that it will interact with. You can very easily get those key bits of information by running strings because that isn't stuff that the computer can optimize for. If there's a file name, the computer, when it's compiling, it can't optimize and shrink the the file name. The file name is the file name. There's no more efficient way of describing the file name. So you can extract that information. You might also get some interesting metadata. Maybe you'll get information about the author. Maybe you'll get information about when the program was created. Your mileage will vary depending on what program you are running strings on. But it's a good starting point, and it might give you some interesting things to look at as you go through the reverse engineering process. Next up, I've got two different decompiling tools. Um, Now, at this point, I'll have to admit that what I said on the previous page about Python is slightly different than slightly off from an interpreted language. So Python here is categorized as an interpreted language. It is, but also you can compile Python to be more efficient. So normally when you run Python, it runs through the interpreter and it'll be less efficient, but it is also possible to optimize the Python program and create what is called a PYC file, which is the optimized Python bytecode, which would go into the Python interpreter, which would run more quickly. So it's both interpreted and also it goes through. It can be compiled as well. There's also JD, the Java decompiler, which can be used to convert a .class file. The .class file is the Java machine code. Sorry, the Java bytecode, which you can then convert back into Java source code. And then next up is GDB. GDB is the GNU debugger. So a debugger is a tool that you can attach onto a running program. So when you run a program, you can attach the debugger onto the running program, and then you can pause the program at certain locations called breakpoints. So when you open up a program in GDB and you run the program, you can say, hey, pause at line 14 as an example. And When the program reaches line 14, it'll pause and you can see the state, the current status of the program at line 14. So you might see information like, um, the variable values. Maybe there's a password that is stored in the variable, and you can grab it using GDB if you pause at a point in time where the password is loaded into memory. You can also use it to make modifications. So let's say, for example, you're trying to bypass some sort of authentication, and there's a variable that keeps track of whether you're authenticated or not. If you use GDB, you can edit that variable and you can say, actually, I am authenticated. Change the false value to a true value and say that I am authenticated. And then when you continue running the program, now the program will think that you're authenticated and you can figure out what happens afterwards. Or maybe the purpose of your reverse engineering was to bypass the authentication, and you're able to do that just by using GDB to modify the state of the program, making it think that you are authenticated. The last two programs on here are Ghidra and IDA. So these are both tools which are disassemblers and also like code visualizers. So you can disassemble the binary code into assembly code, and then Ghidra and IDA will actually show you the paths and the flow of the code execution. So you can see, okay, the program starts at the top here, and then there's a branch. If this condition is true, it goes to the left. If this other condition is true, it goes to the right. This helps you visualize how the program is operating, and it also provides ways for you to annotate what is going on. So you might have a block of text which Ghidra or IDA decompiles, and you will get the assembly code from that decompilation process, and then you can read that and you can say, okay, I'm pretty sure this code is the password verification code, and you can label that block of code password verification, so that you know that that block of text is the password verification, and then you can look through what else is going on through the program and just remind yourself that's what that code does. Oftentimes, when you're decompiling code, you get stuff that looks like gibberish, and it'll take some time to read and understand what it does. And keeping that little reference for yourself there will make it much easier for you when you try to step back and understand the big picture of what's happening in the program. So that sums up all the tools. I'm going to jump into a demo so you can actually see the process of doing reverse engineering. We're not going to go super deep in today's episode. We're just going to start with some basics, and then we might have some future episodes where we get a little bit more sophisticated in our process. But before I go to the demo, let me answer some of the questions that we have in the chat. And if you've got any additional answers, please ask them right now. So Jordan is asking, is strings beneficial for stego problems? So steganography problems where there might be a hidden message inside an image or some sort of video file, some hidden message hidden inside another file. Strings is extremely beneficial for stego problems as an initial starting point. Sometimes it doesn't help at all, but if it does help, it's super beneficial. You might be able to use strings to find information about the author or the program that a file was edited in. Sometimes there is hidden messages hidden inside the metadata that strings will extract for you. And so that's a very good starting point for Stego. So that's an application of strings outside of reverse engineering. We've got another question. Can you have GDB on Kali, or is it just for regular Linux? You can install GDB on Kali or other Linux distributions. It'll work on all of them. So if you have like Ubuntu or Debian or Kali, GDB will work on all of them. You just have to install them. I don't know if it's pre-installed on Kali, but you can definitely get it to run on all the different distributions. All right, let's go into a demo. So right now I've got my Kali machine over here. I'm going to log in. and we're going to solve some challenges from the practice gymnasium. I've got two challenges to look at here, and they're both Python challenges. So in this first challenge, we've got some Python code, and the scenario is that we need to find a password that will authenticate with this program. What I'm going to do first is I'm going to take this code, I'm going to copy it, and I'm going to put it into my own machine here so that I can analyze it and play with it. So let me just create a folder. I'm going to call this Python RE, and this is python1.py. This is a Python file. And I'm going to paste this text into, oops, I'm going to paste this text into my program, my text editor program. I've got too many terminals open. That was from a previous episode. Cool. So now we have this program in a Python file running on our computer. From here, the next step I would highly recommend would be for you to take a snapshot with your virtual machine before you run a program. You don't know what it's going to do. Assume that you have no idea what it's going to do. This could be malware. It could destroy my computer. It could delete all my files. It could be ransomware. I have absolutely no idea what this will do. So you want to take a snapshot of your virtual machine so you can revert back. If something goes wrong, you can revert back and you'll be okay. I'd also recommend doing this in a virtual machine and not your main computer. So if you've got a personal computer where you're doing your reverse engineering and you put this on your main computer and you don't put it in a virtual machine, what happens if it's malware? What happens if it ruins your computer? What about all the files and maybe you've got homework or maybe you've got some other projects and important information on your computer that gets deleted or encrypted because it's malware and it's ransomware. You don't want that happening to you. Be very, very diligent in making sure you create a virtual machine. You take whatever it is that you're analyzing, you put it in the virtual machine, you take a snapshot of your virtual machine, you do all of that before you run the program. And I would actually be even more paranoid in many circumstances and create the snapshot and do all of that before you even like download the file. Because what happens if you accidentally click on it and it runs and now you've got malware on your computer? I will say anything you download from Cyber Skyline will not ruin your computer. We're very cautious about making sure that you're not going to ruin your computer, but you need to establish good practices. So when you do this in the real world, you know this is the process that you have. You know you create a virtual machine, you take a snapshot, then you download the program you want to reverse engineer. You want to be very, very safe because it's better that you take these precautions and you're overly cautious than the alternative where you accidentally run some malware and it ruins your computer. So that is a huge, huge disclaimer. Um, Now, from here, now that we've got the code on our computer, we know that it's a Python file. There's many ways for us to identify that this is a Python file. One way is by looking at the top here, and you can see it says Python. This is actually, because this is an interpreted language, this is I forget the exact name for it, but this is the indicator to the command line, to the shell that will tell it what interpreter to use when it executes this code. We can also see here that it's a .py file, and we also have a description here that says it's a Python script. But if you didn't know that it's a Python script, you can go online and we can just search, .py file. And if I search for that, this will say, hey, a .py file is a program file or a script written in Python. You want to identify as early as possible what programming language was used to generate this file. That will make it a lot easier for you to identify what tool you want to use. So for example, if this was a Java file, we would want to have a Java decompiler that will help us analyze that file. Because this is a Python source code file, knowing that it is Python, we know that we want to run this code through a Python interpreter instead of a JavaScript interpreter or another interpreter, right? So you need to know what language you're working with so that you can use the correct tools to help you analyze it. In this case, we're dealing with a Python file, which means we need to use the Python interpreter to run the program. That's the next step, is figure out how do you actually execute this program. You might download a file which doesn't run on your computer. So you might download a compiled file that only runs on Linux. And if you download it onto a Windows operating system, you can't run the file. So you need to get the correct environment, you need to get the correct tools to actually be able to run that file and see what it does. So we've established this Python. We know we need to use the Python interpreter. Let's go ahead and start doing that. So I've got this program here. If you don't know how to run a Python program, you can go ahead and Google that. The way that we're going to do that is we're going to type in Python and then the name of the Python file. So we've got Python, python1.py. We hit enter. It says invalid args. So it's giving us an error. Why is it giving us an error? Well, let's open up another tab and we're going to look at the code and figure out why are we getting that error. So it says invalid args. Let's look for the invalid args in the program. Invalid args is happening here on line 7. So there, in this code block, we can see that it's going to print invalid args and it's going to return, which basically just ends the program. Above that, we can see there's an if statement, or an if condition. It's checking if len, and if you don't know what len does, you could just come into Google and you can just type in Python len. And you can see here, Python len is the length function, which returns the number of items in an object. So this is length. So we can see that it's checking if the length of sys.argv is not equal to 2, then you get this error. So now we're wondering, what is sys.argv? So I can come in here, I can type in Python sys.argv. Sys.argv, command line arguments. Sys.argv is an array for command line arguments to Python. So the command line arguments are the options that we pass in to this program when we run it. So it's expecting this list to be equal to 2, because if it's not equal to 2, it's going to say invalid args and it's going to return. So we now need to figure out how many args are being passed in. So we could add a print statement here, for example. I can say print sys.argv, and this will show us what we've got. So if I type this in right now, that's this print statement that wasn't there before. So now we can see that currently there's an array. The array is python1.py. So it's expecting 2 items, it's only getting 1. So now we know we need to pass in another value into this program. All right. Now, if I type in this random text, we've got 2 items in our array, and now it's printing out incorrect. This is different. Before we were getting invalid args, now we are getting incorrect. So let's check the program out again. Here's incorrect, and let's go backwards. Let's figure out how did we get to this section where it says incorrect. So we've got this else condition. So there's a condition being checked, and when that condition is not true, then we're printing out incorrect. So let's check for the corresponding condition for this else. It's here on line 14. It's checking builder equals 1000, and the length of the password is 10, and the ord of password 1 is equal to 83. So there's a lot of things being checked here. Let's go one at a time and figure out what are these individual things that we need to meet, these conditions that we need to meet. in order to actually print out correct instead of incorrect. So the process, I'm just breaking this down. The process I'm going through right now is I am analyzing kind of what is just happening here, right? I'm taking a very like naive approach of just saying, I want to run the program, see what happens, and change the behavior and prevent errors from occurring. Another approach that you could take is specifically pinpointing your destination and trying to get to your destination from there. So what I did first was just run the program and see what was going on. Eventually, you will need to take that second step, which is say, all right, I'm trying to get here. In our case, we're trying to get to correct. We're trying to figure out how can we get the program to print out correct. I generally suggest just getting a lay of the land first, then identifying your destination. Sometimes your destination is not immediately available, so getting the lay of the land and just trying things out is a good first approach. I've gotten to the point now where I found out that incorrect is being printed out, and I can see there's an if statement here, and I can see directly below the if statement is the section where it prints out correct. So to me, that is very clearly what we're trying to do, right? The prompt was trying to figure out what password would validate with this program. Having it print out correct seems like a very good like goal. That's our goal, is how do we get the program to get to this line number 15. And now we got to go backwards from there, figure out what is required to actually get to the point where it prints out correct. So we saw that these things need to be true. We don't know what builder is yet, and we don't technically know what password is. We could probably guess what it is, but we don't know what this variable password is, and we don't know what ord is. So let's take these things one at a time. Let's start with builder. Let's work our way up and see if we can figure out what builder means. So if I just read this top down, I can see here, if argv, if the length of argv is not equal to 2, it prints out invalid args. So if it is 2, then what happens is we're setting password equal to argv1. Arrays are 0 indexed. So argv0 is this python1.py, and argv1 is this lkjl. So what we type in second on the command line here, this lkjl, this is the password that we're attempting. So if I type in password, our password is now password. Next, builder is set equal to 0. So builder is just a number. It starts at 0. And then we've got a for loop. For c in password, builder plus equals ord c. So what this line is doing is it is going through every single character in password, and when it goes through the character in each iteration, the current letter is going to be referred to as C. And what we're doing is we're adding to builder. So that's this builder plus equals whatever ord C is. So let's go and figure out what the heck ord is. Python ord. The ord function returns an integer representing the Unicode character. Okay. And you've got some examples here. So ord 5 is 53, ord A is 65, or $sign is 36. So this is taking that character and returning the corresponding Unicode number associated with that character. And for our case, I think the ASCII table is probably like good enough for us to scope our understanding of this. So I happen to know that if you pull up the ASCII table and you take this number 53, you look at the ASCII table, we're looking at decimal 53. Decimal 53 is 5. And then if I am looking at ord capital A is 65, I can come in here. Where's capital A? Here's capital A, decimal 65. So this is basically going to take text that is inputted, that character, and then get the ASCII code associated with that character. All right, that makes sense. So this section here, what it's doing is it is taking all of the all of the all of the characters in the password and it's taking the ASCII codes for those characters and it adds them together. And that's the value builder at the end of this function. At the end of this for loop rather. And after we do that, that's when we do this big if statement. And so it's checking, is builder equal to 1,000? So we know now that whatever password we type in, the ASCII values of every character in that password, when they're added together, they need to equal 1,000. Then the next condition is that the length of the password has to be 10. All right, that's simple enough. And then we also know that specifically the ORD, so the ASCII code of password 1, keep in mind that we're zero index, so password 1 is actually the second character of the password, is equal to 83. All right, so let's piece this together. The valid input has to be 10 characters long. The second character has to be ASCII code 83. And then the remaining characters, or all the characters in the password have to add up to 1,000. All right. So let's first figure out how to, what is ASCII code 83? So if I come here to the ASCII table, I look at 83. 83 corresponds to uppercase S. So we know now that the second character in the password is uppercase S. So let me just type this in for myself. I've got an uppercase S, and then as the second character, and then I've got 1, 2, 3, 4, 5, 6, 7, 8. These are all the characters I don't know about right now. And if I type this in, that's the current working password I have right now. I know it doesn't work. It's printing out incorrect, but we can do something where we edit this code and then just verify if these individual conditions are correct. So with this big if statement, it will only print correct if all three parts of this if statement are correct. We want to verify each one independently, right? So these are the different parts of the lock that are preventing us from getting to our correct answer. It's way easier if we can check to see if we meet all three criteria individually than all three at the same time. Because if there's something wrong with the password, I don't know right now what is wrong with the password. I don't know if the issue with the password is the length. I don't know if the issue with the password is um, the ORD on the second character, or I don't know if the issue with the password is that builder is not 1,000. So what I'm going to do is I'm going to add some prints. I'm going to print builder equal to 1,000. And then I'm going to print len password equal to 10. And then I'm going to print ORD password 1 equal to 83. And hopefully this runs. Let me just give us a quick shot. Did I make a typo? I made a typo. And we can see now that now we can check to see each one of these three conditions individually. We can see here that the first one is false and the second and the third one are true. So already we are 2/3 of the way there. We have the correct length and we have the correct character for that second position in the password. Now we need to figure out how the heck do we make this add up to 1,000. So this is actually some math, and if this isn't intuitive to you at first, you just have to put on like your thinking cap and figure out how would I make these numbers add up to 1,000. We know that one of the characters is 83. So if we take 1,000 and we subtract 83, then the remaining 9 characters have to add up to whatever 1,000 minus 83 is. So let me just do a quick 1,000 minus 83, 917. So the remaining characters have to be 917. Okay, so 917, I'm just going to write a note for myself here. So 917 is remaining 9 characters. We could just divide 917 and that should work for us for the most part. So if I do 917 divided by 9, it doesn't divide perfectly. So what I'm going to do is I'm going to say, let's take this, we're going to take the remainder and we're just going to add that to one character, and then the remaining characters can all be the same. So it looks like if most of our characters are 101, then we might have some remainder, and then we'll stick the remainder in one character. So what if we did 8 times 101? That should give us 808. And if I come in here, I update my notes. I say 8 characters of 101. And then now we need one character of, so we have 808 is what we get when we do 8 times 101. And we need 808 plus this last character to equal 917. So 917 minus 808, we get 109. 109. So what I'm doing is I'm just trying to do the math and figure out, like, how can I get 9 characters to add up to 917, because 917 plus that one character which we specifically need will add up to 1,000. So I just divided 917 by the number of characters that I've got, and then there's some remainder. So I'm like, okay, let's just keep all, like, 8 of them the same, and then one of them will be a different number, which will handle the remainder. And so now we just need to figure out what characters correspond to these values. What character corresponds to ASCII code 101, and what character corresponds to ASCII code 109. And so we can go back to our trusty ASCII table. We've got 101 over here, which is in lowercase e. So let me just go and write that down. This is lowercase e. And then what corresponds to 109? 109 is lowercase m. All right, let's go back here. This is lowercase m. So let me create the password then. So I know that the second character has to be an uppercase S, and that one character has to be a lowercase m, and then the other characters have to be lowercase e. So I can type in m, and then uppercase S, and then 1, 2, 3, 4, 5, 6, 7, 8 e's. And if I've done this correctly, this should be a valid password. So let me copy this and give it a shot. All right, this worked. So now we've got true, true, true instead of false, true, true, right? Here's the true, true, true. Originally we got false, true, true, and at the end it prints out correct. So we made it to the correct to the correct location in the file. We made it to line 22. You might notice that there's actually multiple different answers to this question. You could you could have instead of 101 and 109, these could be 100, and then this final character could be a bigger number. There's like a ton of different possible character combinations that you could do here. They didn't have to all be E's as well. They could all be different characters. It seems like it'd be more complicated to do it that way, but there are actually many different ways that you can um, answer this question to get to the right line here where it validates. But let me just recap what we've kind of done here. We started by copying the file into our virtual machine. I did a snapshot before I did this recording. You should definitely do a snapshot before you do the recording. before you start playing with the file. We try to run the file and try to see like how can we change the behavior, how can we change the flow and where we're getting in with within the file. Once we have a general understanding of what the program is doing, we can figure out what are we trying to get the program to do. We're trying to get it to get to this line. Depending on your objective with reverse engineering, it might be different. In our case, we specifically wanted to get the program to reach a specific line in that program. You might be trying to get a password, which is hard coded in the program somewhere. So instead of trying to get to a specific line, you might be trying to print out the value of a variable. And I guess you do need to get the program to get to that line, but it's specifically with the outcome of printing out a variable. Maybe I make an edit here and print out the password. Or maybe I need to use GDB to debug a program to extract the password from memory rather than editing the source code. In this case, we have the source code because the program is a Python program. But if we were reverse engineering a C program, which was in binary, we wouldn't have the possibility of editing the original code and then adding a line where we print out the password, print out the answer. We would have to actually have to extract that variable directly from GDB while the program is running. Or we would need to like do what we did here and try to guess what the password might be by looking at the code. So this is a very, very simple task that we've had to just read the code and get to the correct answer. I'm going to do another question, another challenge where we have to do some decompilation. So let me first just answer this question so we verify that we solved it correctly. I'm just going to paste that in here. You can see we got it correct. And let me jump into another challenge where we have to decompile a program. All right. So I've got this python2.pyc. I'm going to download it. I'm going to go back to my terminal and I'm going to move it from my downloads, Python 2. Okay. So now I've got this python2.pyc file in my folder. You'll notice that before we were dealing with source code, we were dealing with human readable code. If I attempt to open this PYC file, what do we get? We get all this weird gibberish, right? So I can't see what is happening here. This isn't human readable. This is the machine code, the byte code that humans can't use. We need to convert this into something that a human could use. That's where the decompiler comes into effect. So if you try to read a binary file or some sort of machine code or byte code, and it looks like this, you're going to want to look for a tool that can help you decompile it. I will go online. I'll search Python decompiler. Well, actually, first, let me take a step back. How do you know that this is Python? I could go type in PYC file. Come in here. You can see PYC files are created by the Python interpreter. When a PY file is imported, they contain the compiled bytecode. All right, so let's see decompile PYC file. And then from Stack Overflow, you can see someone recommending using uncompile 6. So I've got uncompile already installed on my computer here. So I can actually use uncompile PYLE 6 on Python 2. And this will actually give me something that's human readable, right? So when I tried to read the PYC file, it was just binary gibberish. I couldn't understand it. This actually gives me something that's human readable. And so I can save this output into python2.py. This will now be my source material. And I've got this program here. So again, our objective with this is to find input that will validate properly. So because we did that prior challenge, we can actually skip a bit. We already know what this part does, right? We've seen this before. This is checking for the length of the arguments. We already figured that out. Password is equal to argv1, counter is equal to 0. This is very, very similar to what we just looked at. We're also seeing now that there's this vals equals list, and you get this thing here. I don't quite know. This just seems like random characters to me. And then we've got some other code. If length of password is not equal to the length of values, then print out incorrect. Okay, so we know now that the length of this text here is the length of our password. And then we've got a for loop or a while loop. While counter is less than the length of the password. We're getting the ORed. We're adding 7. If this x is greater than z, we're going to subtract 26. And then we do character x. So let's first run the program. There's a lot of steps that I'm skipping through right now. This is a lot to keep a track in my mind all in one shot. So I want to run the program and just see what happens because this is too much to keep track of. So we're going to run Python 2 invalid args. We need a password. That's incorrect. Let's look at our Python 2 file. And we know that the length has to be the same as this. So I'm just going to copy it. And if I copy it, I'm going to have the exact same length. Cool. It's still incorrect, but I want to make sure I'm at a different incorrect. So I'm going to call this incorrect 1. I'm going to call this incorrect 2. And this will let us know which one, line 19 or line 26, is the line that we are reaching. So we've got incorrect 2, which means that we're at this section here. All right. So now let's try to piece together what the heck is happening. We figured out that this section here is just checking for the length. So this is the meat and potatoes of what we're trying to do. So while counter is less than length of the password, this looks like you've got a counter starting at 0. At the end of this, you've got a counter plus equals to 1. It looks like this is going through every single character in the password and then running this code here. We've got a variable called x, which is equal to ORed of the password that we type in plus 7. And then if this is greater than the ORed of z, minus equals 26. So this might seem familiar to you if you just did crypto, but this is a shift cipher. So what is going on is that the program here is taking the character that you've typed in and it is moving it forward 7 characters. And if the result means that you go past z, it subtracts 26 so that you loop back and you go back into the alphabet. So you don't go past z, you loop back and you'll continue. So this is a shift cipher, actually a plus 7. And then now it just checks if the character of x, so let's just go and do a quick search for this, chr python. This method, chr, returns a character from an integer that represents a Unicode character. So this is the opposite of ORed. So ORed will take a character and give us a number. CHR will take a number and give us a character. So what is happening here is that after we have shifted the password by 7, we're now checking to see if that shifted password is equal to this vals. Character for character, right? So it takes the first character, it does the shift plus 7, and then it checks after we shift your character by 7, is it equal to t? And then it'll do the next character in the password and check to see after we shift it plus 7 if it's equal to f. So you could write code to solve this, but I'm going to take a shortcut because I know that this is specifically a shift cipher. So I know that I know this website rot13.com, and this will actually allow us to shift a password. And so if I take this and I copy it and I paste it in here, this will allow us to shift the password. The program here is taking our password and shifting it +7. And when it shifts it +7, it is expecting it to be equal to this value. So we need to go backwards. We need to take this value and go, instead of forward 7, we need to go backward 7. And that should give us the password. So I'm going to, so rot13 will move us forward 13 characters. So we need to think about how to get back. Instead of doing +13, we need to do -7. How would I do this? I'm putting myself on the spot here. Um, Let me just fiddle around with this. So let me just go back 7. 1, 2, 3, 4, 5, 6, 7. So 13 minus 7 would be 6. Okay, that doesn't look like. Let me just try this. We're trying to move 7. So actually, rot7 would move us +7. If I go to the end of the list and I go back 7, that will give us the opposite effect. So let me start at 25. 1, 2, 3, 4, 5, 6, 7. We do rot19. Hey, this actually looks like something that is reasonable here. So let's just copy this and then plug that into our little program here and see if that works. All right, so we validated this properly. So a one way to think of, so you might be wondering, why is it rot 19? The reason why it's rot 19 is that a rot 26 would loop you back to where you are, right? And we actually want to go backwards by 7. So if we start at rot 26 and then we go back by 7, that will give us the desired effect, right? A rot 26 would get you all the way around the alphabet and back. And if we want to go, instead of forward, we want to go backward, we start from a rot 26 and then we do rot 26 -7. That gives us rot 19. So rot 19 is the equivalent of going back 7, shifting back 7. All right, so we've now solved 2 reverse engineering challenges, right? We've had the source code trying to figure out, how do I get the password on that first question with just the plain source code, the plain text. And then we had that second question where we got a compiled Python PYC file, and we figured out how to decompile that PYC file and get the password again. A lot of this is really trying to guess what is it that what the developer is trying to do, right? I can see here that um, the code for this while loop, if I took it at face value and I was like, okay, let me try to shift every single character back 7 and have this like very strict interpretation of the code and try to step by step it, it's going to be very long and tedious. But I can kind of guess the behavior here, right? If I'm reading this, I'm like, why would I do a -26? And I'm like, well, there's 20. I know that there's 26 characters in the alphabet, and Z is the last character in the alphabet, so it looks like this is looping around. I am interpreting what this code is intending in order to create a shortcut, because me understanding that this is a loop for when you get past to the end of the alphabet and you got to loop back, I can do things like go onto rot13.com and use rot13.com to solve my problem, rather than actually doing the math on every single character. So being able to like interpret and understanding what the developer is trying to do will actually help you with your reverse engineering pretty substantially. it's a skill that you develop through practice. It's not something that I can really give you a process to immediately do right away. But as you look through more code, this will be a little bit easier. All right. So that's all the demo that I had today. I've got a couple more questions to answer here. If you've got a question right now, please ask us right away. Um, all right. We've got someone asking, how can we tell if a program installed ransomware or some malware? Um, you don't necessarily know. It might be immediately obvious if you start seeing it's the behavior that you're looking for. So after you run the program, you're looking at the behavior. Um, are there pop-ups on my screen? Are files missing? Is there these weird programs that are running on my machine now? It's the behavior that you're looking for that will immediately tell you whether you've run some ransomware or malware, or past that initial behavior. If you look at the code, you see what it does, and you have to make the judgment call on whether you think that's malicious or not. So if you see code in here that's like deleting things, that's probably malicious. But in this case, this code isn't deleting anything. It's just checking some text. It doesn't seem malicious. It's not malware. So you have to run it, see what it does, or look at the code and make an interpretation of whether or not you would consider that to be malicious. Jordan's asking again for the decompiler tool. So the decompiler will depend on the language. I used uncompile for Python. There is JD, the Java decompiler for Java. There's a lot of different tools out there for different languages. I'm not going to enumerate them. What I would recommend is go onto Google, type in, X specific language decompiler, and that will help you find the right tool. Be careful with those decompilers as well, because you might download something that says it's a decompiler, but it's actually malware, right? So this is why it's so important to do this in a virtual machine and take a snapshot. So if you accidentally download something that messes up your computer, you can revert it. All right. That looks like all of the questions. I'd like to thank you all for joining us today on another episode. I want to remind everyone that these episodes are guided based on the feedback that we get from the audience. So if you've got other ideas for what topics you want us to cover, please tell us in the chat. Leave a note in the comments. We'll be sure to do future episodes that will cover what you all are interested in. But if you're just joining us today, make sure that you go back to our YouTube channel. We've got a huge playlist of all of the episodes that we've done. And if you are a little bit weak on coding, we've got some episodes there for you that you can go and catch up on. But thank you all once again for joining us today. Hope we catch you in a future episode, and take care.